All right, here we go with our next section. This is called double angle identities. This is going to be section 4.7 on page 262 of your workbook. This comes right on the heels of what we did last time was sum and difference identities. And in fact, our derivation for sines double angle and for cosines double angle is just going to use exactly that. We'll use exactly what we did last day. And it starts off by saying for sine of a plus b, the rule is that's equal to sine A cos B plus sine B cos A. What happens if we let A equal B? If we let A equal B, then what we have is sine of A plus B is actually equal to sine of A plus A. We're letting A equal B, and it's equal to sine of A plus A. Now, following through with our rule, for our rule says sine of A plus B is equal to sine A cos B, but if B and A are really the same thing, then this ends up being sine A cos A. Plus, the second half is now going to be sine A cos A also. Adding those together, this ends up being 2 sine A cos A. But what does this represent? What does this sine of A plus A represent? This is sine of 2A. This altogether is on our formula sheet. It's our double angle identity for sine. It's called double angle because it's going to take that angle A and it's going to double it. So if our angle A was 20 degrees, this would now be sine of 40 degrees. And that's what we're working with here. Okay, so for cosine, what happens? For cosine, if we do the same sort of thing, for cosine of A plus B, if we let A equal to B, so remember our cosine formula looks a little different, cos A cos B minus sine A sine B. And if we do this, then what happens? Then cosine of A plus B equals cosine of A plus A now, because they're equal to each other. And what is that equal to? If we follow our formula, this is cos A sine A sine A, or simplifying, this is A squared, cos squared, minus sine squared. So that represents cos of 2A. So here's our double angle identity for cosine. Now, we have one for sine and we have one for cosine. But we can use our Pythagorean identities to change what this cosine one looks like. So we have just one formula for sine double angle, but we're going to make more than one formula for cos double angle. Where this is going to come from is, remember that cos squared A plus sine squared A is equal to 1. There's our basic Pythagorean identity. If I subtract sine squared from both sides, this becomes cos squared A is equal to 1 minus sine squared A. And if I did it the other way, I would have solved for sine squared, then this is equal to 1 minus cos squared A. And we're going to take each of those and make a second and third manifestation of our cosine double angle formula. So it looks like this. So if we take cos 2A, our new rule says that's equal to cos squared minus sine squared A. And if we replace, let's do this one first. Let's replace cos with 1 minus sine squared A. And then we're subtracting sine squared A. And we end up with 1 minus 2 sine squared A. This ends up being part 2 of our cosine double angle. 1 minus 2 sine squared A. Part 3 ends up being this. So if we start with cos 2A is equal to cos squared A minus sine squared A. And instead of replacing cos A like we just did in part 2, in part 3 we're going to replace sine squared A. And this ends up being equal to cos squared A minus, in brackets, 1 minus squared A. When we do our subtraction, we are subtracting negative cos squared A, gives us 2, positive 2 cos squared A minus 1. That ends up being our third version of cosine double angle. So we have 3 of them. You don't need to memorize them. They're on your formula sheet. And so what you need to be doing is you need to make sure that you're familiar with each of them so you kind of know what you're looking for when you look to your formula sheet and trying to put this together. All right, tangent. So tangent, it ends up being pretty simple to create. It's probably just as simple as the sine one is to create, and you could take your sum of your sum identities for tangent, and it just ends up being equal to 2 tan A divided by 1 minus tan squared A, if we let A and B be equal. So not a big deal to create that one. Those are all on your formula sheet. And let's move forward. So now we're going to use these in our trigonometric proofs. When we are proving our trig identities, that's another tool that now we have in our chest. Now, our clue to look for this, our strategy to look for this, is whenever we see double angle stuff going on in this proof, we know for sure we're going to be using one of our double angle identities. In this case, left side 2 tan x over 1 plus tan squared x. My right side is 2x. Now we've talked about how our strategy should be work with the more complicated looking side, and that is true. We for sure will be working with the left side of this, but that said, we know from our double angle identities, for this to look anything like this, for sure we're going to have to swap this out, and let's call this 2 sine x cos x. There's our double angle identity for sine. So let's just start off with that one step on the right side, and that's what we're aiming for. So our first strategy here, our first thing that we're going to notice is that denominator is one of our Pythagorean identities. That 1 plus tan squared is secant squared x. Look into your formula sheet and you would find that. Now let's change everything into sine and cos. This ends up being 2 sine x over cos x. There's your tangent. And I'm dividing by secant squared x, which is the same as multiplying by the reciprocal. The reciprocal of secant squared x is cos squared x. I'm going to make another column worth of stuff. I'm going to still relabel this as my left side so as to not confuse our reader. And this ends up being 2 sine x over cos x times cos squared x. If I divide out one of those factors of cos x, we end up with 2 sine x cos x, which ends up being equal to our right side. And therefore, LS is equal to RS. And we have proven it. We should state our non-permissible values, our restrictions, and what can't happen. Well, the fact that we have tan x is present tells us that cos x can't equal 0, which is here and here. We also have this denominator, we have 1 plus tan squared. can't equal 0. So therefore, 1 plus tan squared x cannot equal 0. Therefore, tan squared x cannot equal -1. That can't happen. Tan squared x can't ever equal -1 because you can't square a number to give you a negative. And so really our only restrictions come from here. So we would say that x cannot equal pi halves, where n is an integer. I probably want to be maybe a little more careful about showing my steps in here. Let's see here, what else, how else would I represent that? I would state that because tan x, we have tan x, which is sine x over cos x. Therefore, cos x cannot equal 0. X cannot equal halves. And then I make that general statement about that. All right. Next one. Sine theta plus cos theta all squared is my left side. My right side is 1 plus sine 2 theta. Yeah, the left side is probably a little more complicated looking, but the fact that we've got 2 theta in here, that actually is something that we're for sure going to have to deal with again. So this ends up being 1 plus 2 sine theta cos theta. Again, for sine theta, we don't have a choice. We only have one double angle identity for sine. For cosine, it's going to open up a little bit and give us a little bit more choice of what we're using in here. All right, let's look at the left side. The left side, sine theta plus cos theta, all of it squared. Resist the urge. Do not square sine and square cos and call it done. That is not what's happening. That's sine theta plus cos theta in brackets times sine theta plus cos theta again. We have to distribute this, and it leaves us with sine squared theta plus 2 sine theta cos theta plus cos squared theta. Now, if we look at to see what's going on the right side we have 1 plus 2 sine theta cos theta, and we have that 2 sine theta cos theta right here. So it's going to give us something to aim at. So that should maybe remind us then, well, those two together have to be 1. Well, that is our Pythagorean identity. Sine squared plus cos squared is equal to 1. And so therefore, that's my next step. Let's call those parts 1. Let's leave the 2 sine theta cos theta alone. And now this is equal to the right side. Therefore, LS equals RS, and we're done. We have no restrictions in this one because this is just sines and cosines. Your domain of those is all real numbers. We don't have anything in denominators that would make us look at dividing by 0 and seeing what we have to restrict. All right. Left side being 2 over 1 plus cos 2x. My right side, secant squared x. Not too much to do with that right side right now. We could, of course, call it 1 minus cos squared, or 1 over cos squared x. That's true. But let's use one of our cosine double angle formulas. The 3 cosine double angle formulas. Cosine of 2x is equal to one of 3 different things. The first one is it's either equal to cos squared x minus sine squared x, or perhaps it's equal to 1 minus 2 sine squared x, or it's equal to 2 cos squared x minus 1. So we're going to use one of these three identities. Now, keeping in mind that this right side right now, this secant squared x, that is 1 over cos squared. So we're probably going to want to express this left side just in terms of cosine squared. And so we're not wanting to use this. Sine x doesn't show up anywhere in our right side. We don't want to use this one. Sine x doesn't show up anywhere in our right side. What we probably want to use is that third one. And this ends up being 2 over 1 plus 2 cos squared x minus 1. We simplify this. This ends up being 2 over the positive 1 plus negative 1, add to 0. And this is 2 over 2 squared x. The 2's divide away. And this is 1 over squared x, which is equal to secant squared x, equal to the right side. So we're pretty much done. Let's just T's and dot our I's. And so we would say, therefore, left side equals right side. To state restrictions, we should state that cos squared x cannot equal 0. That's really, it's from at this point, or it's from the right side, that cos squared x can't equal 0. We don't really know what this looks like, but once we made this swap and called it cos squared x, and we swapped out our double angle, it really just ends up being this because it's equal to that. And so cos squared x can't be 0 is really our only restriction in what we are left with is x cannot equal pi halves, 3 pi halves. Square root, right? Cos x 0, square root of 0 is 0. So maybe I should state that next is ends up being x cannot equal pi halves and pi is an integer. So we've seen that before. So we're starting to see that that ends up being a big piece of what we're doing in here. Every time we have a restriction, they look pretty similar to each other, but we need to be careful. Number 2, give the exact value of 1 minus 2 sine squared of 22.5 degrees. 22.5 degrees isn't anything that we really know exact values for. We know all of our multiples of 30s and 60s and 45s, and that's really it. If we're working in degrees, that's not one that we know, of course. But hopefully you're recognizing that 22.5 is half of 45. This question is going backwards, and often we would start with cos 2 theta is equal to 1 minus 2 sine squared theta. But in this case, we're given this. And in fact, theta, that theta here is 22.5 degrees. And so what do we have over here on the left side, what it's equal to? Well, it's going to be equal to double that. And so 1 minus 2 sine squared of 22.5 degrees is equal to cosine of 2 times 22.5 degrees. So we're just making use of this formula, but we're going backwards. We're going the other way with this compared to what we were doing before. And if that's the case, this is equal to cosine of 45 degrees for 2 halves. Number 3. If tan theta is 5 over 12, And we are between 180 and 360 degrees. Let's state our exact value. Okay, let's start off with this part first about tan theta is 5 over 12. So let's, before we even dive into part A, let's look at this. Theta is between 180 and 360, tells us that we are in 180 less or equal to theta less or equal to 360 degrees. Therefore, we are in quadrants 3 and 4. I kind of like to do these with Roman numerals to be consistent. Quadrant 3, quadrant 4. So we're down in the bottom half just by saying that 180 is less than theta is less than 360. Tangent is 5/12, which is positive. So therefore, between quadrant 3 and quadrant 4, we would choose that we are in quadrant 3. And let's draw this in quadrant 3. If tangent is 5 over 12, tangent is y over x, or it's sine over cos. And it's going to look like this. Now, technically that's negative 5 over negative 12, which still ends up being positive. That because we're in quadrant 3, that is what we're dealing with. Hypotenuse, we've been calling r for the radius. And so therefore, negative 5 squared, negative 12 squared, r squared. 5 plus 144 is r squared. R squared is equal to 169. R is equal to plus or minus 13. We need to state this, but we know that r is a scalar. So let's state that r has to be greater than 0. Therefore, r is equal to positive 13. We need this because if we're evaluating cosine, then we need to know what r is in this case. Now we can go ahead and do question A. Question A says cosine 2 theta. We could use any of our manifestations of this. It doesn't really matter which one we're going to use. Cos 2 theta ends up being 2 times cos theta, cos squared theta, minus 1. Remember that cos squared theta really just means cos theta, all of it squared. That's just our notation for it. And what do we know? Well, we know that cosine theta is x over r. And so our x is negative 12. Our r we found is now 13. And so we have 2 times negative 12/13 squared minus 1. Ends up being 2 times 144 over 169. I'm going to subtract 1, but I'm going to change that 1 into a common denominator. And this ends up being 288 minus 169 over 169. And we do our subtraction and we get 119 over 169. There's our answer for A, 2 cos theta, or cos of 2 thetas, all right? Sine 2 theta, remember we don't have choice with sine of double angle. We only have one formula for that. That's equal to 2 sine theta, cos theta. And looking at our triangle now, this is 2 times negative 5 over 13 times negative 12 over 13. We multiply this all out and we get 120 over 169. Moving on. Question number 4. We have an expression 1 plus cos 2 theta over sine 2 theta. We're wanting to simplify this and say which it's equal to. Whenever we see this kind of in a question, we see, okay, we have this expression, and then it says where theta is not equal to n pi over 2, where n is an integer. Again, I usually use z for integers. Alberta Ed chooses to use I. Most universities would use Z if you were in a math class. Right? So if we are simplifying 1 plus cos 2 theta over sine 2 theta. Oh yeah, so this part really is just telling you about your restrictions, what happens because of the denominators. And so that tag on the end, we don't really need to worry about that. We're just going to be simplifying that. It's really just expressing our restrictions for us. Let's go ahead and see what we can do with 1 plus cos 2 theta over sine 2 theta. I would probably start with dealing with this denominator first. Before we get too far into cosine 2 theta, because we don't have any choice of what sine 2 theta looks like. Sine 2 theta we know is going to be 2 sine theta cos theta. Perhaps that's going to give us some direction about which manifestation of cosine double angle we're going to use. Again, we could use cos squared minus sine squared thetas. We could use 2 cos squared theta minus 1, or we could use 1 minus 2 sine squared theta. Again, we could probably choose any of these. I'd probably stay away from the first one. I don't know what I would do as a next step. Well, it's going to take an extra step if we use the first one. But if we use this second one, the positive one and the negative one are going to divide out. So maybe let's use that. So 1 plus 2 cos squared theta minus 1. That numerator becomes 2 cos squared theta over 2 sine theta cos theta. We divide out a factor of cos theta from top and bottom. Let's also divide out a factor of 2, and this ends up being cos theta over sine theta equal to cotangent theta. And so for cotangent theta, here it is right here. So our answer is A. Now, would it have been different if I had chosen one of the different manifestations of cosine law? If I had chosen to use 1 minus 2 sine squared theta or something else? Well, let's just check that out. Let's see what would happen here. If I used, let's do this in a different color so it stands out. This was going to be 1 plus 1 minus 2 sine squared theta. If I used that instead for cos 2 theta, this is still over 2 sine theta cos theta. What do we have in the numerator? We have 2. We are going to add those ones together. So 2 plus, not plus, it's going to be 2 minus 2 sine squared theta all over 2 sine theta cos theta. If I common factor a 2 and divide it out top and bottom, I'm left with 1 minus sine squared theta upstairs over sine theta cos theta. And then just keeping in mind that by Pythagorean identity, 1 minus sine squared is just cos squared theta over sine theta cos theta. And so we still get to cos over sine. It takes a little bit little extra steps to get there. Again, we could have gotten there from cos squared minus sine squared and using that first double angle cosine identity. Anyway, either way we get there. Question number 5. Point A, x comma y, is the intersection point of the unit circle and the terminal arm of 145 degrees in standard position. The coordinates of point A to the nearest hundredth. So the fact that it's asking to the nearest hundredth is a clue that it's not going to be an exact value. We're going to decimalize this. We're going to need our calculator for this. Be aware with this whole unit of whether you're working in degrees or in radians. By default, most of the time we are working in radians, and unless it says something specifically about degrees, then doing stuff in radians. In this case, we're going to need to shift our calculator back to degree mode. And we're going to do this. Now, 145 is about there. There's 145. Keep in mind that when we have coordinates, when we have x and y coordinates on our unit circle, the x is just really the cosine. So this coordinate really is cosine theta, comma, the y is sine theta. And so our point x comma y is really just that, cos theta, sine theta. And so therefore the coordinates of point A to the nearest hundredth is really just going to be cosine of 145 degrees, comma, sine of 145 degrees. And that's it, because cosine is the x and sine is the y. And therefore, we push those into our calculator. I believe you get negative 0.82 for cosine. You get positive 0.57 for sine. That should make some sense, the fact that we certainly are in quadrant 2, so our x should be negative, our y should be positive, and that's it. Question number 6. Given a point on the unit circle, determine the value of sine 2 theta. If our point is 0.56 and 0.83 for x and for y, well, then what do we know? We know that sine 2 theta is equal to sine theta cos theta. And for what we were just saying in the previous question, sine theta is just going to be our y. It's important that we're given that it's on the unit circle. And so our sine is 0.83 times our cosine, which is 0.56. And I multiply that together. And so sine 2 theta is 0.9296. And this last one, given a point on the unit circle is 2k comma negative 3k. Determine the value of cos 2 theta. So whenever we're given coordinates, we probably want to start off with a sketch of what's going on. 2k comma negative 3k. This is the point 2k comma negative 3k. That means that x value is 2k, our y value is negative 3k. And it looks like this. By Pythagorean theorem, we can figure out what our r value is going to be. We're going to need r for cosine. And so therefore, 2k squared plus negative 3k all squared is equal to r squared. This leaves us with 4k squared plus 9k squared equal to r squared. Gives me 13k squared is equal to r squared. But what do we know about r? The fact that it's on a unit circle. R is equal to 1. R equals 1. So therefore, 13k squared is equal to 1. K squared is equal to 1/13. K is equal to plus or minus the square root of 1/13. We don't know if it's positive or it's negative, because technically it could be over here too, right? This could be 2k, and this could be negative 3k. If k is a negative amount, that could be the case. All right. Last part of this is now cosine of 2 theta. Now let's use, again, we could use really any of these. Cosine 2 theta is going to be equal to cos squared theta minus sine squared theta. Because it's on the unit circle, then cos theta is just the x, it's just 2k. So we've got 2k squared minus negative 3k. Our y values are sine. And when we square it, it looks like this. So this ends up being 4k squared minus 9k squared is equal to negative 5k squared. Now, we have the fact that k is equal to plus or minus square root of 1/13. So therefore this is equal to negative 5. And then this plus or minus root 13. Squaring it. We're squaring it does two things. It gets rid of the radical, so it's just 1/13. It also takes care of the fact that it's plus or minus. Either way, whether it's positive or negative, 1/13, when we square it, it just ends up being times positive 1/13. So this ends up being equal to negative 5 over positive 13. And that's it. That's our last step. So cosine 2 theta is equal to that. And there's our final answer. All right, I hope this helps. If you have any questions, please make sure you mention that. And good luck with this. Thank you.